Two vectors describe a plane in 3D space, but they're tilted toward each other at some awkward angle. Projections get messy, decompositions become painful. Now picture swapping them for two perfectly perpendicular directions that describe the exact same plane without losing a single point. The Gram-Schmidt process does exactly this. The entire algorithm rests on one move. Subtract the shadow of one vector from another. Here's the building block. Vector projection. Projecting vector B onto vector A finds the shadow of B along A's direction. The formula is the projection of B onto A equals A transpose B divided by A transpose A all times A. The numerator, A transpose B, is the dot product of A and B. The denominator, A transpose A, is the squared magnitude of A. This fraction scales A to produce the shadow vector. Now the critical part. Subtract that shadow from B. The result is a residual vector, the part of B with no component along A. This residual is perpendicular to A. Two vectors are perpendicular, also called orthogonal, when their dot product equals 0. Let's verify. A dot the residual equals A dot B minus A dot the projection. Expanding, we get A dot B minus A transpose B over A transpose A times A dot A. The A dot A in the numerator cancels with A transpose A in the denominator, leaving A dot B minus A dot B, which equals 0. So the residual captures only the genuinely new direction that B offers beyond A. This single operation, subtract the shadow, keep the perpendicular residual, drives the entire Gram-Schmidt process. Let's work through this with concrete numbers. Take A equals the vector 1, 1, 1, and B equals the vector 1, 0, 2. These are linearly independent. Neither is a scalar multiple of the other, so together they span a plane in 3 dimensions. Step 1. Accept the first vector without modification. Set capital A equal to lowercase a. So A is 1, 1, 1. Step 2. Remove B's shadow along A. Compute A transpose B. 1 times 1 plus 1 times 0 plus 1 times 2. That gives 1 plus 0 plus 2, which equals 3. Next, compute A transpose A. 1 squared plus 1 squared plus 1 squared, which is also 3. The projection ratio is A transpose B over A transpose A, 3 over 3, which equals 1. Now subtract. Capital B equals lowercase b minus 1 times A. Component by component, 1 minus 1 gives 0, 0 minus 1 gives negative 1, 2 minus 1 gives 1. So capital B equals the vector 0, negative 1, 1. Step 3, verify orthogonality. Compute A dot B, 1 times 0 plus 1 times negative 1 plus 1 times 1. That gives 0 minus 1 plus 1, which equals 0. The dot product is 0. A and B are orthogonal. We replaced our skewed pair with two perpendicular vectors that span the same plane. That 0 isn't a coincidence. Here's why it's guaranteed every single time. Let's take A transpose B and prove it always equals 0. Start by substituting the definition of B. B equals B minus the fraction A transpose B over A transpose A times A. Now distribute A transpose across this expression. A transpose B equals A transpose B minus the fraction A transpose B over A transpose A times A transpose A. Now look carefully at the second term. We have A transpose A in the denominator and A transpose A being multiplied in the numerator. These A transpose A terms cancel each other out completely. What remains is simply A transpose B minus A transpose B, which of course equals 0. The formula was engineered so that the dot product vanishes every time. This isn't lucky arithmetic. The cancellation is structural. It's guaranteed to work for any vectors A and B, no matter what numbers you plug in. Orthogonal vectors A and B point in perpendicular directions, but they aren't unit lengths yet. Orthonormal means both perpendicular and magnitude 1. To finish the process, we divide each vector by its magnitude. The magnitude of A equals the square root of 1 squared plus 1 squared plus 1 squared, which equals the square root of 3. So Q1 equals 1, 1, 1 divided by the square root of 3. Now for the magnitude of B, the square root of 0 squared plus negative 1 squared plus 1 squared, giving the square root of 2. So Q2 equals 0, negative 1, 1 divided by the square root of 2. Both vectors now have length 1. That completes our orthonormal basis. 2 vectors down, and the same idea extends to 3. Take a third vector C, linearly independent from A and B. We already built orthogonal vectors capital A and capital B in the previous steps. To find capital C perpendicular to both, we subtract C's shadow onto capital A, then subtract C's shadow onto capital B. The formula is capital C equals C minus A transpose C over A transpose A times A minus B transpose C over B transpose B times B. Geometrically, this works in 2 stages. First, project C onto capital A and subtract. This removes the component along A. The result is an intermediate vector that may still have a component along B. Second, project that intermediate result onto capital B and subtract. What survives is the piece of C perpendicular to both capital A and capital B, the only fresh direction. And here's why the 2-stage approach gives the same answer as the full formula. Since capital A and capital B are already orthogonal to each other, projecting the intermediate vector onto B gives the same coefficient as projecting the original C onto B. The B transpose A term is 0, so nothing interferes. Finally, normalize this vector to unit length, and we get Q3, orthogonal to both Q1 and Q2. The pattern we've been building generalizes beautifully to any number of vectors. Here is the general formula for the case step of Gram-Schmidt. The orthogonal version of vector v sub k equals v sub k minus the sum from j equals 1 to k minus 1 of the projection of vk onto each previously computed orthogonal vector vj. In other words, you subtract every projection onto every direction you've already established. Let's see how this expands for each value of k. For k equals 1, it's simple. v1 orthogonal just equals v1. The first vector is accepted as is with no projections to subtract. For k equals 2, v2 orthogonal equals v2 minus the projection onto v1 of v2. And that's 1 projection subtracted. For k equals 3, v3 orthogonal equals v3 minus the projection onto v1 of v3 minus the projection onto v2 of v3. Now we subtract 2 projections. For k equals 4, v4 orthogonal equals v4 minus the projection onto v1 of v4 minus the projection onto v2 of v4 minus the projection onto v3 of v4. That's 3 projections subtracted. Notice the pattern. Each new vector subtracts more and more shadows, 1 for every orthogonal direction already established. One important detail. This process is strictly sequential. Each step depends on all of the previous orthogonal vectors. You cannot skip ahead or orthogonalize vectors in parallel. The first vector is accepted as is, and every subsequent vector subtracts projections onto all the ones that came before it. A common misconception: Gram-Schmidt changes the subspace. It does not. The original vectors A and B span a specific plane. The orthonormal vectors Q1 and Q2 lie in that exact same plane. Every point reachable by combining A and B is also reachable by combining Q1 and Q2. The column space, the set of all linear combinations of the columns, is preserved. The plane hasn't moved, only the signposts within it have changed. Same subspace, better coordinates. Gram-Schmidt bridges any linearly independent set to an orthonormal set spanning the same subspace. This bridge is foundational. Let's see why. The entire algorithm is one recipe with 3 steps. Step 1. Accept the first vector, v1. Step 2. For each subsequent vector vk, subtract its projections onto all previous orthogonal vectors. Step 3. Normalize each result to unit length. This recipe directly powers QR factorization. Every matrix A can be factored as Q times R, where Q has orthonormal columns, built directly by Gram-Schmidt, and R is upper triangular. Beyond QR, Gram-Schmidt enables cleaner least square solutions in data fitting and gives numerical computations better stability. Let's return to the big picture. The subspace never changes, only the basis describing it becomes orthogonal, unit length, and far easier to work with. Watch as the original skewed basis morphs into the clean orthonormal basis, all while staying on the same plane. Subtract each shadow, keep the residual, normalize. Same space, better coordinates.